the chemistry, the lesson 3 will involve alkenes. Now, we have already looked at the chemistry of alkenes, and we see that alkenes, alkenes, and alkynes belong to one general homologous series of what are referred to as hydrocarbons, but separate specific homologous series. Now, I've already said that hydrocarbons are those organic compounds that contain carbon and hydrogen only as the only elemental composition. Now, the difference between alkenes and alkanes is based on only one factor: the existence of at least one carbon to carbon double bond. And earlier on, we had talked about hybridization. And we say that where we have only carbon to carbon single bond, we have sp3 hybridization, meaning that in alkanes where we have we only have single bond, the general hybridization is sp3. Whereas in alkenes, at least in two carbons or in one carbon, one carbon must be two carbons must be sp2 hybridized, because they are joined together by a double bond for a molecule to become alkenes. Now, an important point to note is that when we are looking at sp2 hybridization, we say that between the carbon and carbon, one of the bonds will be a pi bond, while the other carbon to carbon double bond will be a sigma bond. Now, unlike sigma bonds, pi bonds are fixed bonds. They are dimensional. They can either be x, y, or z. Looking at a 3-dimension, you either have a y dimension, x dimension, or a z dimension, and they are fixed. So they are rigid bonds and do not allow movement. Okay, so the important thing here is to note that a molecule is identified as an alkene if it has at least one carbon to carbon double bond, but it can have more. Now, the simplest of the alkenes is ethene, which has two carbon to carbon two carbons, so that the double bond is between the two carbons. Because you cannot have a single carbon and have a double bond. Therefore, the simplest is one with two carbons. Now, the difference, the difference is only in the existence of the double bond from alkenes. Now, in terms of nomenclature, we start with the nomenclature, is that alkenes are named in a similar way as aldane alkanes. Only that, whereas the prefix in naming of alkenes is similar to alkanes, the only difference is that in the suffix, whereby instead of using the suffix a and e in alkenes, we use the suffix e and e in place of a and e, so that in a two-carbon alkene, the name is ethene. Now, if you have three-carbon alkene with only a single double bond, then it is propene. Now, in this case, we only need to replace the a and e with e and e. But note that when it comes to larger alkenes, the position of the double bond is significant in that one molecules with the same carbon numbers and even only a single double bond may have different chemical and physical properties depending on where the double bond is positioned. In that case, when you are naming alkenes, you have to indicate the position of the double bond if it is not certain where it should be. But for example, a molecule like alkene and propene, you don't need to name the positions because they can only be in one position. Now, looking at examples in nomenclature, we have this molecule. Now, this has 1, 2, 3, 4, 5 1, 2, 3, 4, 5, meaning that it is a pentene. However, you cannot just say pentene. You have to indicate the position of the double bond, because here you have seen the double bond is in position 2. It could have as well been in position 1. So, and this would have been two different molecules with varying chemical and physical properties. So in this case, when you are naming, you indicate the position of the double bond by indicating that it is in position 2. So you call it 2-pentene. But because you may have other fixes, usually we use 2 in between the prefix and the suffix. So the most preferred way is to call it pent2-ene. Now, if you look at this molecule here, now, usually you look, when you are giving the main chain, you have to consider to include the double bond. So in that case, you start counting 1, 2 from the position of the double bond up to the longest chain, which is a 5-membered chain. You could have gone this way or that way. The result would have been the same. And so this one becomes ethyl. In position 3, you have an ethyl group. So 3-ethyl, 2-methyl, 1-pentene, or you can call it 3-ethyl, 2-methyl, pent1-ene, because you have to indicate where the position of the double bond is. So could look at one more example where we have a double bond again at position 1, but you have 2 methyl groups in a 6-membered carbon. So in that case, it is you count from 1 to the methyl groups are in position 5-5. So you call it 5,5-dimethyl 1-hexene, or you can call it 5,5-dimethyl hex 1-ene. Now, if you may have not only a single double bond, but you can have 2 or more double bond. Now, just like we said, when you have more than one constituent in a molecule, we use the prefixes di, tri, etc. depending on the number. So if you have 2 double bonds, then you add di in front of ene to indicate that it has 2 double bonds, and then it becomes a diene. It has 3 double bonds. You use the prefix tri, indicating 3 in front of ene, becomes a triene. For example, this one has 2 double bonds in position 1 and in position 3, and it's a butene. So it is but1,3-diene, or 1,3-butadiene. So the longest chain applies in alkenes, just like in alkenes. So if in this case of this one, the chain contributing the largest number of double bonds is considered. So the double bonds should ideally be included in looking for the longest chain to name. And in this case, this one, instead of looking at it this way, we look at it that way, and we look at it as a 1,4-diene. In that case, we call it, the side group is a propyl. So it is 3-propyl, 1,4-pentadiene, or you could call it 3-propyl pentan 1,4-diene. Now, we can also have cyclic alkenes, and we consider the position of the double bond as the first position unless otherwise. And in this case, this one becomes a cyclopentene. And if it has only 1 double bond, you don't need to indicate 1, because it will always be in position 1. If, however, you have 2 double bonds like this one, you can jump this one, then it means that you have to count in a manner that gives the double bond the first position. And in that case, giving the lowest position, so it is, though you could start here, that would give the number a very high number. But if you start here, you'll have the double bonds at the lowest possible position, 1, 2, 3. So this is 1 and this is 3. And then the side group in position 5. So in that case, this one becomes 5-methyl-1,3-cyclohexadiene. So I think looking at the examples that are given, you can be able to understand generally the naming. And so long as you understand the nomenclature of alkenes, then it becomes easy to understand the nomenclature of alkenes. So now the next point we go to, we have already stated that the double bond has one sigma bond and one pi bond. And the pi bond is has fixed dimension, meaning that it is rigid, it cannot move. And that brings a problem in or an issue in alkenes, in that there is no movement around the carbon-to-carbon double bond, and this brings about a phenomenon that is referred to as cis-trans geometric isomerism, a form of isomerism where you may have molecules with the same molecular formula. We already said that isomerism is about having the same molecular formula, but different connectivities or orientation in space. In this case, this is about orientation in space, and that is what we can refer to as stereoisomerism. So cis-trans geometric isomerism is a form of isomerism, referred to also as geometric isomerism, in that you may have molecules with the same molecular formula, similar connectivity in terms of atoms, but the orientations of groups being different. For example, let's consider but2-ene. Now, this is but2-ene. Now, at the position of the double bond, you have a hydrogen and a methyl groups on either carbon bonded. Now, because of lack of movement around the double bond, if the methyl groups happen to be on opposite sides, like this one, that is, one is on top, the other one is at the bottom, then they are said to be counter to one another, and that such an isomer is referred to as a trans isomer. That is, similar groups are trans. They are in different sides of the double bond. So this, though it is a but2-ene or 2-butene, it is different, and you have different melting points from where, from this one, where the methyl groups are on one side. So we say that when the similar groups are on one side, they enhance one another. When they are on opposite sides, they cancel the effects of one another. And that means that the effects of the groups in trans 2-butene is weaker than the effects of the groups in cis-2-butene. Cis, because the groups are on the same side, and these ones will have different physical and even myodring-faring chemical properties. You can also have a situation where you have, for example, a chlorine bonded to propene, position 1. Again, because you have two hydrogens on either carbons bonded to the double bond, then you can look at hydrogen as a basis of the cis-trans isomerism, where you can look at are the hydrogens on the same side or on different sides. So where you have the hydrogens are on the same side, on opposite sides of the double bond carbons, then you have a trans isomer, and where they are on the same side, you have a cis isomer. Now, so generally, in the simplest term, geometric isomerism in alkenes can be looked at as either in terms of cis or trans isomer. However, you may have a situation where you have double bonds, where you have different groups joined to double bond, such that on every side, no two groups are similar. So in that case, the simple explanation of two groups being, similar groups being on one side of the double bond or on different sides of the double bond does not apply. However, still, the way the groups will be arranged will matter. For example, look at 2 bromo, 1 chloro, 1 fluoroethene. In that case, you have the carbons of the double bond being joined to 4 different groups. So in that case, you cannot talk about 2 groups being on the same side. However, still, isomerism will matter on the way those groups are joined. So the simple methods of considering cis and trans does not arise, does not occur here or does not apply, but rather we use differentiation of the type of geometric isomers in terms of Z and E, what we call ZE type of isomerism. Instead of using cis and trans, we use ZE as indicators of the type of isomerism, so that groups that are bonded to the carbons of the double bond are identified by their RMM or RAM, relative atomic masses, or relative molecular masses, so that priority is given to the highest molecular mass. So in this case, these 4 groups, you have bromine, fluorine, chlorine, and hydrogen. The bromine has the highest molecular formula. So it will, chlorine has the highest. Bromine has the highest molecular formula, so it will be identified as 1. Chlorine has the second highest molecular formula, so it will be identified as 2. This is the way you have. And then fluorine should have a higher molecular formula than fluorine is 3. But however, you only need to identify. The reason, the way you see numbering being 1, 2, is that on every carbon you have to identify which one is priority. In case of chlorine and fluorine, chlorine has a higher relative atomic mass, so it is given 1, as opposed to fluorine 2. Bromine higher than hydrogen, it is 1, 2. So in that case, if ones are on the same side, then you consider it as a cis. If ones are on trans sides, then you consider it as a trans isomer. And in that case, this one, because in the first example, the number ones are on the same side, so this one becomes a Z isomer. Z, 2 bromo, 1 chloro, 1 fluoro. So a Z isomer is where priority groups are on one side, while an E isomer is where priority groups are on opposite sides. So nomenclature, where you have different groups joined to carbons of the double bond, then isomerism, the geometric isomerism, is rather labeled as EZ instead of cis trans. And it is based on priorities, and priorities are based on the higher the RLM or RMM, the higher the priority. So you can look at examples. Let's look at this one. This example, a simple example here. Now here we have iodine, chlorine, bromine, the methyl group. Now, of course, for iodine and chlorine, iodine is lower on the periodic table in terms of group 7 than chlorine, meaning that it has higher relative atomic mass, and therefore iodine should be given priority 1, chlorine should be priority 2. Now, if you look at bromine and methyl, we look at the first elements, carbon and bromine. Bromine should be given priority 1, carbon 2. In that case, the larger groups are in 1. So this one, if the larger groups are on one side, then it is a Z. Z, 2 bromo, 1 chloro, 1 iodo, prop, 1 in. So you can look at other examples that are given, and they have been given the corresponding geometric labeling. Now, alkenes, generally, in terms of physical and chemical properties, is that alkenes, just like alkenes, are insoluble in porous solvents. They have low melting and boiling points compared to their counterparts. That is inorganic compounds. And this is because similar to alkenes, intermolecular bonds is the van der Waals force. And van der Waals forces are weak forces. Although the interatomic bonds are strong, the covalent bonds are strong, you note that the intermolecular bonds in alkenes, just in alkenes, are weak, and therefore alkenes have lower melting and boiling points than corresponding inorganic compounds of related relative atomic. Now, comparatively, if we compare alkenes to alkanes, alkenes relatively have lower melting and boiling points than alkanes. And the explanation is that although we have similar forces joining molecules of alkenes and alkanes, the position of the double bond brings about poor packing, is that it brings about, there is some level of bedding at the position of the double bond. Considering that the double bond exhibits a trigonal planar kind of geometry, it brings about an uniform distribution in terms of geometry, and therefore poor packing and lowering of melting and boiling point. So in general, we can say that if you are given an alkane and alkene of related relative molecular mass, the alkene would generally be expected to have a lower melting and boiling point. So again, C2 to C4 are general gases at room temperature, C5 to C15 are liquids, while the higher ones are semi-solids or solids. So in terms of solubility, just like alkanes, because of lack of polarity, alkenes will not be soluble in polar solvent, but are soluble in nonpolar solvents such as benzene, chloroform, etc. So you have seen they are more volatile than alkanes, and due to poor packing, they are less dense than water. And the same applies to alkanes. They are boiling points, just like in alkanes, will increase with increasing carbon numbers, or what we say, increasing relative molecular masses. Now, we have already talked about physical property. Now we go to chemical properties. Now, we have identified the difference between alkanes and alkenes as the existence of a double bond, that is one or more double bonds. Now, the difference in terms of chemical reactivity is that in alkenes, the greatest or the highest or the most probable position of reaction is the position of the double bond. And this is because due to existence of two bonds, there is a high electron density at the position of the double bond, and that is the position where reaction takes place. Usually, the reactions of alkenes involve breaking of the double bond so that you end up with a single bond. And breaking of the double bond involves groups that are seeking electrons attacking the carbons bordering the double bonds. So the type of reactions that occur in alkenes are what we call electrophilic addition reactions. Groups that are seeking electrons attack alkenes at the position of the double bond. And because of that capacity to react at that position, alkenes are generally more reactive than alkanes. And looking at some of the types of reaction, one of the reaction, combustion reactions, we had already looked at combustion reactions in alkanes, and though not indicated here, combustion reactions in alkenes will take place similarly to combustion in alkanes, and the result in excess oxygen is formation of carbon dioxide and water. So alkenes can also be used as fuels. Although they burn with luminous flame, they are more suited because there is a poor reaction at the position of the double bond. Now, looking outside the carbon-oxygen reaction, general what we can call combustion, alkenes can react with hydrogen at the position of the double bond, but that can only happen in the presence of metal catalysts, mostly nickel catalyst or other metal catalysts, but the most important is the nickel catalyst. And the result is that the hydrogen adds at the position of the double bond so that the double bond is broken and you end up forming an alkane from an alkene. That is what is known as hydrogenation. Now, hydrogenation converts alkenes to alkanes. And you're saying that alkanes have higher melting and boiling points than alkenes. So it means that hydrogenation results in molecules that have higher melting and boiling points. And therefore, you may find that you are converting, say, liquid to solids, and so on. So, and that is important, particularly, for example, in the oil industry, where liquid oils, by addition of hydrogen at positions of double bonds, are converted into saturated oils, which are solid, which is referred to as hardening of oils. Now, you'll find that the amount of hydrogen that adds to the double bonds, to alkenes, depends on the number of double bonds. So again, the amount of hydrogen that adds to alkenes can be an indicator of the level of unsaturation. Addition of halohydrin. Now, in presence of water and in the presence of halogen molecules, a molecule with both an OH group and a halogen group, referred to as a halohydrin, can be formed. For example, if it is bromine, you'll form a molecule where a bromine, one atom of bromine adds at one of the carbons of the bond, and the OH from water adds to the other, what we call, refer to as halohydrin. In this case, it's a bromohydrin of that molecule. Generally, we'll move to addition of acids of molecules of the same form of HX, because looking back, these molecules like sulfuric acid can be seen as molecules that can give hydrogen ions and anions. So the reaction in such molecules is similar, follows a similar formula to all molecules that have the formula HX, where hydrogen in the molecule, the H in the molecule, molecular formula represents a hydrogen. In that case, these are acids. Molecules that can be defined as acids, where the defining factor is a hydrogen proton, are referred to as Bronsted-Lowry acid. So, generally, alkenes will react with Bronsted-Lowry acids, and including going back to sulfuric acid, so that there is a hydrogen and a sulfate anion on one side, so that hydrogen adds onto one carbon of the double bond, and the anion adds to the other carbon of the double bond. So that is the general reaction when you react alkenes to Bronsted-Lowry acid. However, that addition is not in any way, does not follow any formula, but follows specific step. In that addition, the hydrogen of the Bronsted-Lowry acid will join to the carbon atom that has the highest number of carbons. Meaning that if you are adding an acid to an alkene, so that you have an anion and a hydrogen ion that are to join. So the anion will add to one carbon, the hydrogen will add to the other carbon. The hydrogen will always ordinarily add to the carbon bearing the higher number of hydrogen. So the hydrogen will seek the carbon with higher hydrogen. And the rule that says that when you add, so you read this, that the rule that states that when an acidic molecule adds to an asymmetric alkene. That is an alkene where in the carbons bearing the double bond, the number of hydrogens differ. An if they were the same, then it would be asymmetric. So adds to an asymmetric alkene. The major product is the one in which the hydrogen atom attaches itself to the carbon atom already carrying the larger number of hydrogens. Now that rule that states that hydrogens will always add to the carbon bearing the larger number of hydrogens ordinarily is what is referred to as Mcaveeney's rule. So, for example, if you look at a molecule like this one, let's look at a molecule like this one. You have propene. Carbon number 1 has 2 hydrogen. Carbon number 2 has only 1 hydrogen. Now, if in the addition of water, if you look at water as a Bronsted-Lowry acid, which consists of a hydrogen ion and an OH anion, then the hydrogen should add to carbon number 1, which has more hydrogen, following the Mcaveeney's addition. So the end result will be a molecule which has the OH group in position 2, or propan 2 all, instead of propan 1 all. Now, the explanation to that, to the Mcaveeney's rule, is that the resulting intermediate, in the addition of a Bronsted-Lowry acid, there is an intermediate in which the hydrogen adds first, and then the anion adds second. The intermediate in which the hydrogen adds first is a more stable intermediate than the one in which the hydrogen adds to the carbon having the higher number of hydrogen. Is a more stable intermediate than the one in which the hydrogen adds to the carbon having the less number of hydrogen. We say that the carbonium ion resulting from addition through Mcaveeney's process is more stable than the one which would otherwise result. Now, it is also important to note that the following the addition that follows Mcaveeney's rule only happens, generally happens. However, under certain conditions, the reverse process can happen. If, for example, you have hydrogen peroxide, the Mcaveeney's rule is reversed, so that if water was adding here and you had in the presence of peroxide, the hydrogen would add to the carbon having the lesser hydrogen in carbon 2, and the OH would add to carbon 1. That is referred to as an anti-Mcaveeney's addition. Now, the other type of reaction involving alkene is the addition of ozone O3. In the addition of ozone, 2 atoms of oxygen, O2, will add to one of the double bonds and join the carbons, and the other one to the other, so that you have what we refer to as an ozonide intermediate, which breaks down into the resulting ketones or aldehydes, depending on the type of molecule that you have. Now, alkenes are easily oxidized in the presence of mild oxidizing agents, e.g. hydroiodate and other related oxidizing agents, into the corresponding ketones and aldehydes. In the presence of strong oxidizing agents, for example, potassium permanganate or potassium dichromate, there is, ketones will not easily be oxidized further. But if you had an aldehyde, then it will further be oxidized into the corresponding carboxylic acid. And this reaction is a great distinguisher between alkanes and alkenes, in that alkanes generally will not be oxidized, and if only where we have tertiary branched alkanes. And in that case, even the oxidation can only be carried out using strong oxidizing agents. So the decolorization of the oxidizing agents can be able to distinguish between alkanes and alkenes. Then we go to the process of polymerization. Now, polymerization is where small molecules like ethene react in the presence of a catalyst, so that the many small molecules join to form very large molecules. Now, this the process of polymerization is very important in chemistry and in industrial chemistry, in that most plastics and related compounds, which have found major applications in the area of industry, for example, in the formation of polythene papers, polythene bags, PVC materials, which are in large use, are formed by joining together through the positions of double bond of alkene molecules to form very large molecules, which are generally solids, but which can easily, in many circumstances, be molded, referred to as plastic or polymers. That polymerization will involve joining of thousands of molecules, up to tens and even thousands and tens of thousands of molecules. Now, looking at this is a process where we are looking at formation of alkenes. How are alkenes formed? There are different ways of formation of alkenes. One is if dehydrohalogenation of alkyl halides. If you have an alkane which has where one hydrogen has been substituted by a halogen. Now, if you remove the halogen atom together with the neighboring hydrogen, and this can be done in the presence of alcoholic alkali solutions, then you end up with formation of an acid molecule and an alkene. So dehydrohalogenation of alkyl halides is one way of formation of alkenes, and this happens in the presence of basic solutions of alkali hydroxides in alcoholic solutions. So depending on where the halogen atom is, you can form different types of alkenes. For example, if it is in position 1, then the dehydrohalogenation will take place in carbon 1 and carbon 2, etc. Alcohols can also be converted to alkenes in the presence of sulfuric acid and heat, in the presence of relatively concentrated solutions of sulfuric acid, and in heat you can convert alcohols into alkenes. So that is another way of preparation of alkene. The method basically involves removal. The method of dehydration of alcohols generally involves removal of water molecules, so that you have a water molecule and an alkene as the end product. Also, you can have removal of halogens, neighboring 1,2 halogenal organic compounds can be converted, halogenal alkenes can be converted into alkenes using metal catalysts like zinc, where the metal catalyst joins to the two halogen atoms, so that the carbons, the neighboring carbons, are left with a double bond and that is in the formation of alkene. And here are various examples. And this happens in the presence of ethanoic acid. So tests, qualitative tests of alkenes, there are a number. One, we had said that alkenes are easily oxidized by oxidizing agent. So in the process, they decolorize the oxidizing agents. So for example, potassium permanganate is purple. So if you add an alkene, as it gets oxidized, the potassium permanganate itself will get reduced, and the color will change from purple to colorless. So that can differentiate between saturation and unsaturation. So generally, that kind of test will differentiate between an alkene and an alkane. Another test is that alkenes, unlike alkanes, will react with the halogens, even in the presence of darkness. And alkenes will decolorize, for example, bromine water, in the presence, dissolved in carbon tet in the dark, because it will react through addition reaction. The bromine will be reacted, and so it will be removed from the solution, and therefore the solution will change from the red color of that is due to bromine to colorless. This cannot happen with alkane. So that kind of a reaction can also differentiate between alkenes and alkanes. And as a simple test, so you put bromine in carbon tet, and you add an alkene in one test tube, and another you add in another one you add an alkane. The one with an alkene will react even in the dark, but the one with an alkane will only react in the presence of sunlight, because we saw that alkanes only react with the halogens in the presence of sunlight through free radical addition, elimination reactions. Now, so that brings us to the end of lesson 3. And for this lesson, we end with exercise questions. One, the first question is, alkenes are saturated hydrocarbons, while alkenes and alkanes are unsaturated hydrocarbons. Explain the term saturation and the term unsaturation. For that, because I had not mentioned, I'll give you a clue in that saturation means more, and the more the number of hydrogen, if you have the maximum number of hydrogen, then you can talk about saturation. If you have less than maximum number of hydrogen, you can talk about unsaturation, and you can answer that by looking at the general molecular formula. 2, complete the following reaction and give the IUPAC name. So this is a reaction between an alkene and hydrohalogeno acid, that is hydrogen bromide. And so you can consider the reaction and considering Mcaveeney's rule. So point number 3, explain Mcaveeney's addition of an acid HX to an unsymmetric alkene. You can go and look at the rule. Write the major product of the following reaction. So there are reactions, and considering what we have covered in lesson 2, then you can be able to come up with expected products. Thank you.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.